Hi, welcome to the Calculus 3 assignment practice series. And we are in the unit vector calculus. And this is the assignment number 4. And this is the second video about this assignment about the line integrals. So from the previous videos, and we did several problems about the line integrals over the scalar field. And today, the second video, we're going to try to do several problems over the about the line integrals over the vector fields. Okay. All right. So now let's go ahead and go to our assignment worksheets here. Okay. So I'm going to start doing the first problems I'm going to do is the problem number 17. I really like the problem number 17 and 18. And it's kind of like give a very good ideas what is about this line integrals over the vector field. Okay, so the 17th here, so it says here, right? So let's say the vector, let the F is be the vector field, and the C is the vertical, C1 is the vertical lines from the segment, the -3 to -3, 3. So I want to determine whether this integration, the vector field dot dr over the C1 is positive, negative, or 0. Okay, so let's take a look. So let me see what is my C1s here. So C1 is like from here to here, right? So this is what the C1s here, starting from this point and go to this point here, right? So this is my C1s here. Okay, so if you take a look, the C1, and then you see here, this is how do you push, so how do you integrate over, kind of you push the particles here. And then, the vector, look at the vector is turning in this direction. So that means that the way you travel, right? So kind of the travel on this curve is in the same directions as where your vector, or you can think about this is a force, how that go. So what is the C1s here? So what do you think the C1 going to be here? So that means, if I'm traveling the same directions as my force applying to me, so that means I'm expecting to see what I did a positive work, right? Okay, now let's take a look at the part B here. So the part B, it says is C2 is a counterclockwise oriented circle with radius is 3, centered origin. Okay, so basically, so I have, this is my next curves here, right? So this is my green curves here, similar like this, right? And so this curves here, this is C2 here. But I'm doing what? I'm doing the counterclockwise, right? So counterclockwise, that means my curve, I'm traveling while integrating here, or you can say you're moving your particle, you travel the counterclockwise here, right? So if you take a look, when you travel the counterclockwise, so you go this way, the green one, you go this way, but your vector, your force turn to the opposite direction. So what you think the work has been done for these particles here, it will be what you expect what negative work have been done, right? Okay, so now let's take a look at the same ways here, right? Same ways here. So for the 18th here, this one's here. So for the 18, and oh here, where they have, okay, so let me get rid of this, right? Okay, so for the 18 here, okay, so for the 18, we do the same. You said, okay, so the field, I have a C1 and the C2. C1 is this way, I go this way, right? It's go the counterclockwise. So I want to see, you know, whether the line integral, so this is the C1, the F dot dr, all right? So it's a positive or negative or zero. C1 is going this way, looks like it's going to the same direction as your, you know, your force turning. So what I'm turning here, so I'm doing the positive work, right? Okay, so then the C2 is this curve here. So it's go like this way, so clockwise. So if you compare the C2s here, so this is the C2s here, this is the F and the DRs here, right? So the C2s here, because, you know, you go this way and but your force turn other way. So I expect the C2 is doing a little bit more the negative work, right? Because they go into the opposite directions here. Okay, so those problems are pretty, I think it's a pretty good concept problem, get you a good understanding about what is line integral. Then the next few problems, those are just very, very mechanical. You just plug into our formula, then you change everything to be a function of t, and you can integrate that. Okay, so I'm going to show you, you know, do one problem here, see, you know, we can do that because this is the problem. So we say I want to find the work done by the force field. Okay, so it's x squared y e x. And I have a particle move along the parabola x equal to the y squared plus 1 from 1, 0 to 2, 1. So this is the problems here. So we do not have a parametric form. So now let's take a look at how do I do the parametric forms here. And now you see here x equal to the y squared plus 1. So probably it would be easier if I set y equal to t. Now what is the x here would be the t squared plus 1 here. Okay, because I set y equal to t, so what is my t domains here? Will be depends on the y's, right? So that's why my t is from 0 to 1. Okay, so now I'm going to do the same thing. After you find it, then the same thing, this is dx dt. So what is here is 2t. This is dy dt. What do you have here? Is 1 here, right? Okay, so now I know the work has been done, so it will be integrating. Now the goal is change to everything to t's, right? Okay, so the t I know is 0, 1. So the first thing is here, I'm going to look for x squared, right? So x squared, so what is the x squared? Is t squared plus 1, and is what? Is dt, right? Dx is here, right? Because we know the integration, if you do the integration like the c, the p, q, x, y, dx, and then this is q, x, y, dy's, correct? Okay, so now I know this one going to be what? Dx. So what is dx? Is 2t. Okay, then plus, right, the qxy. So what is here is yex. So it will be t e x. This is t squared plus 1, correct? And then here, what is here? This is dy. So I need to use dy's here. So what is here is times 1. Then the whole thing here is dt's here, right? Okay, so now for this ones here, this will be the 0, 1, and this is 2t squared plus 1, and the plus t, the t squared plus 1. So the dt. This part is pretty easy, and this part is not hard, not too bad. So what you do here, this part you do a u sub, right? You do a u sub, you set u is equal to what? T squared plus 1, then you'll be able to get the integration. So I got the integration. So the final answers here, it will be 1/2 e to the square minus 1/2 e plus 7/3 here, right? So it's pretty easy. So even like for this province here, they did not give you the parametric form, but the function is easy enough. You'll be able to set the parametric form easily, okay? All right, so now let's continue to do the one other problem. This problem is very interesting. It combined several things we learned before, so that's why I like to do this. Okay, so the first things they tell me, they say, hey, I have a position functions of object, and this object is mass is m, and the t is, so this is my position function. This is the RT, AT square I plus BT cube J, T is from 0 to 1. Okay, so I want to find the force acting on the object at a time t. Okay, so I think from the physics 101, what is the force here? Force is the mass times what? Accelerations, correct? So it's mass times acceleration. But right now I'm just having vector form. So this is the position function. So from the, we know if you take the derivative of the position function, what you have here, you will have the velocity functions, right? So the velocity function, okay, so the derivative here, this is 2at, right? Then this is 3bt squared. So this is the velocity function. So this is the velocity vector function. Now I need to have a's, right? So the a is the acceleration. So how do I get the a's here? So at, we know also if you take the velocity function's derivative will give you the acceleration. So what is the accelerations here? Will just be the 2a, and then you take the derivative again. So this is 6b what? 6bt's, right? So this is my what? This is my acceleration function. So the part A, they say, what is the force, acting on the object at time t? So it will be what? It will be just the m times 2a 6bt's, right? So this will be the 2ma I plus 6b and tj's, right? So this is what we said, this is your force field, right? So it's a force vectors. So now the second part here, they say, what is the work done by the force during the time interval? That means what is done by that, right? So now I said, okay, so the work has been done will be what? Will be the force dot product, you travel along this path here. So now I can say, okay, so t is from where? 0 to 1. All right, so here this is a 2ma, right? Okay, so this is a 2ma, and then the derivative of r prime is 2at 3bt squares here. So what is here? So you will have the 2ma, so your 2ma, 6b, and t dot product, right? Dot product r prime t. So what is r prime t? So 2at and 3b, what? T squared. Ta-da, right? We change everything to t again. Even in this the vector force field, we be able to change everything, convert back to the t. So now you do the dot product. So this is 0, 1. So this is 4ma squared t, correct? And the plus 3 times 6 is 18b squared and what? T cubed, right? Now you do everything to dt, and the b, m, and a, they are all what? They are all constants. So after you figure, so this will be the 2ma squared plus, right? So plus 9 over 2, and this is mb squares here. right? So this is how much work have been done and by this force field, okay? And so I think that's it for this section. It's pretty easy. After you understand the concept, and then the calculations is very mechanical and pretty easy. I hope the few problems I did here and help you to get a better understanding about how to do the remaining problems here. Okay, that's it. It's nice to talk to you and looking forward to go over our next, the next topic here. Okay, bye.